Okay, and so a horizontal metal bar oriented east-west. So we've got north, and remember that the North Pole of the Earth is not magnetic north, it's actually magnetic south, but that means that our B field on Earth points towards the North Pole. So we've got east, south, west. So a horizontal metal bar oriented east-west drops straight down, so we're dropping it straight down. And an EMF develops between the ends, which end is positively charged. So the easiest way to rationalize through this is to consider the force on a charge due to its velocity. So it'll be V cross B, and this is the force on, depending on the charge, so if it's negative, it'll be in the opposite direction. So this will be the force on this will give you the force direction on a positive charge. And so we can use the right-hand rule here, where we, it's likely not possible to see me, but where we point our hand, see if I can draw a hand here, our hand in the direction of the velocity, and then hold our thumb out, I guess. The hand was okay at first, but now it's grotesque. There we go. Hold our palm in the direction of the B field, or we can say that we curl our fingers in the direction of the B field, and then the thumb will point in the direction of the force. And so if we do this for this problem here, so the velocity is pointed into the page, the B field points north, and so our force on a positive particle must be this way, meaning oppositely, a force on a negative charge, so that's the force on a negative charge, will be towards the west end, so the electrons will be pushed towards the west end, meaning that this east end will develop positive charge, and the west end will develop negative charge. But the question asks, which end is positively charged, and that would be the east end. Okay, so here in the solution, pointing the thumb along the motion of the metal bar, which is out of the page. I would not say that, but that sounds more like it's moving up. Fleming's right-hand rule, the direction would be along east to west, which shows the direction of current. So thumb along motion of the bar. Well, in any case, the motion's opposite, which I just wouldn't agree with, but it still gives the east end, so that's Solution's the same, but the motion's different, which is confusing to me, but I'll say the solution is correct. I'm not sure if Fleming's right-hand rule applies here. I believe it's for forces on charge-carrying objects, or current-carrying objects, I mean. So I believe it gives you the motion of a current moving through a magnetic field, not necessarily the current due to motion. But I'm just going to say